Hello everyone, my name is Xinlin Li from Huawei Noarzak Lab. Today I'm excited to present our paper DenseShift toward accurate and efficient low-bit power of 2 quantization, which was accepted at ICCV 2023. Let's begin with the research background and motivation. The deployment of deep neural network on edge devices has become increasingly challenging due to the rising computational and memory demands. One promising solution is the power of 2 quantization or logarithmic quantization. It simplifies the computation by replacing expensive multiplication with a more hardware-friendly bit shifting. And recent work has indicated that if an AI accelerator uses power of 2 quantization, it can lead to smaller chip area and reduce power consumptions. However, achieving a high accuracy with power of 2 quantized models remains a challenge. In our previous work, S3 training, we identified that the quantizer-based training is ineffective for low-bit discrete weight due to weight freezing issue. Weight freezing refers to latent weight values clustered around the quantizer's function threshold during training. This issue makes it hard for the backprop gradient to move the latent weight across multiple intervals to its optimum solutions. To address this, we introduced the S3 training algorithm. This approach projects the discrete weight into an expanded higher dimensional optimization space, allowing for easy transition between discrete values and facilitating the optimization of loss function. In this work, we aim to further enhance the power of 2 quantization, especially in low-bit scenarios. We introduced DenseShift, a refined power of 2 quantization algorithm, eliminating zero value in its weight space and offering several advantages. Firstly, this design maximizes the weight encoding space usage, especially at lower bits, providing a larger model capacity using the same bit width. We've adapted the S3 training algorithm for DenseShift, and our experiment results using ResNet 18 on ImageNet shows significant accuracy improvement in 2-bit and 3-bit models. Plus, our new training algorithm is more user-friendly. It can seamlessly replacing full precision convolution layers. Another advantage of our 0-3 weight design is that it enables power of 2 quantization inference using floating point activations efficiently on general hardware such as CPU. To the best of our knowledge, all existing power of 2 quantization methods requires quantized activation for efficient bit shifting computation. However, activation quantization introduces extra limitations. For instance, you may need to handle additional quantized and dequantized layers during training and inference. Furthermore, in many instances, it's hard to quantize activation due to its distribution, such as large language model. These drawbacks prevented the widespread adoption of power of 2 quantization. In this work, we designed an efficient method for computing power of 2 weight with non-quantized floating point activations. By leveraging the format of floating point numbers, we can directly use fixed point addition instruction for computing the multiplication between a floating point number and a positive or negative power of 2 values. Related work shows that fixed point addition is far more cost-effective than floating point multiplication. Our new approach overcomes the limitation of existing power of 2 quantization with floating point activations. What even better is that with the 0-3 shifting design in the DenseShift networks, floating point multiplication can be efficiently computed with one single integer addition instruction. Using these techniques, we achieve a 1.6 times speedup in the half-precision dot product computation on ARM CPU. This is the first time the power of 2 quantization shows speedup on a general-purpose hardware outside of ASICs or FPGA. Lastly, we dive into adapting the DenseShift network training scheme for transfer learning tasks. We noticed that the S3 training encountered significant accuracy drop and instability in transfer learning contexts. To counter this, we developed an initialization technology. Thanks to our approach, our 3-bit power of 2 quantized model matched the performance of full precision model on various tasks, including object detection and semantic segmentation. In conclusion, we propose DenseShift network with zero-free weight space and size-scale decomposition training for constructing high-performance low-bit power of 2 quantization with high training and inference efficiency. For the first time, power of 2 quantization support inference with non-quantized floating point activation and show performance gain without dedicated hardware such as ASICs or FPGA. Our extensive experiment on vision and speech tasks demonstrate that the low-bit shift networks can achieve comparable performance to the full precision model. Thank you for your attention.